Um, ouais, plutôt. Mais je veux pas trop. Ouais. Ah, si quelqu'un d'autre veut partager, c'est peut-être ça, d'accord. Donc là, so hello everybody. I will start by recalling one of the basic things about these lectures. So we will make reasoning on many structures, but all of them are have the shape of trees. Okay, there could be very simple trees or more complicated trees, sometimes very complicated trees when we go to what we call inductive relations. This is not for today. This is for probably next week. So, but the general thing to remember is that what we said before is that, so when we have some kind of trees, let us say it's trees with this kind of shape, ternary trees, for instance. Okay, and okay, I stop at some point. When you want to program on them, you need recursivity. You know all that. And so recall that if you are able to compute the value at some point, at the leaves, then you can, and if from the leaves, or in general from any subtree, you can go to the immediately the tree which includes the tree before. So you are able to construct step by step the result until the root. Okay? So this is the general shape, and the same holds also for reasoning. If you are able to prove that some property holds on leaves, okay, so let us say proof like this. So if something holds on leaves, and then from the leaves, you can somebody. Qu'est-ce que je peux faire là? Maybe. Okay. Sorry for the interrupt. So the idea is each time from if you are able to conclude that if something holds on subtrees, then the property will be inherited on the enclosing tree. So you see that step by step you can prove this. So proving is exactly the same as computing. Okay. So for computing, it is called recursive programming, and for when you are doing proofs, it is called proof by induction. It is exactly the same mechanism. Okay, so we will use that intensively on a number of structures. So we have already seen some easy examples on binary trees. Yesterday, I think, when you reversed twice a binary tree, you get the original binary tree. The proof is quite easy. So now this principle can be used as well on all kinds of trees we will meet. So one of them are, some of them are called AST, abstract syntax trees. Okay, so the basic structure for reasoning on, or yes, reasoning on, or doing compilation, for instance, programs, how to represent programs. We represent them using AST. And okay, so I will show you okay, some examples later. Other examples, a little bit simpler, are lists. Okay, so lists are also kind of trees. You can draw them. Okay, if we use OCaml-like syntax, it is like something like this. So you have either what we call the empty list, which is written this way, or it's just a notation. Sometimes we could use something like nil, and sometimes we can introduce some notation for kind of shorthand for this. Okay, and the node here typically is called the cons. Okay, so this is the infix notation. So, for instance, if you have a list of a nut or integer in OCaml, say 2, 1, 4. Okay, so you see that the list is just a kind of tree with only actually one branch. Okay, here we have three branches at each node for this one. For AST, we will see generally binary nodes. So list, okay. So we have one component here, which is just an element, but nothing recursive here, okay. And the last factor, which is still simpler, are just natural numbers actually. Okay, so natural numbers representing it this way, so it is a bit like list without information. And instead of cons, the constructor is called S. And the last constructor is called 0. So S means successor. So this is basically the simple mathematical representation of natural numbers. I don't claim that it is efficient in any way. If you use this representation in OCaml, for instance, for each time you add one, actually you use a pointer, so it's very it wastes a lot of memory. So the question is not about efficiency; it is about reasoning. Okay, so what the important point is that all the induction principles you get for AST, ternary trees, lists, or not, etc., all the induction principles are based on what I said before. And the basic example is induction on natural numbers. If you use this general induction principle on natural numbers defined like this, you just get the simple mathematical induction on numbers that you learn at school. Okay, it's just a special case. Okay, so I prefer to myself to introduce the general idea, and then you just instances. And when you go to more complicated examples, like next week, what we call inductive relations, or kind of trees, but with more information inside, the same principle still applies. So we will see that next week. Okay, so we will start with AST in order to get used to this kind of reasoning. List, we will need them. We need them for representing states, for instance, and natural numbers. Okay, it will be the opportunity to understand the real thing which is behind the notation we used until yesterday and Monday. Okay, so actually when you write this is actually an illusion. It is not at all in Coq, not in OCaml, but in Coq, it is not. You have nothing which is a small element called 2. Okay, you could imagine that natural numbers are a kind of big enumerated type, but that's not the case. It is just actually this is the notation for this one, successor of 0. Okay, you have to know that because the behavior of Coq and all functions of natural numbers are all the operation like plus, multiplication, and so on are defined using recursive programming on this structure. So this makes things very basic, and you can reason just by the induction we know. Okay, application of this general induction principle. Okay, so that's all for the whiteboard today, at the moment. So I will share the screen again. So I hope this works. Okay. So basically, I put two files on my web page. So the first one on the top here is there for has been there for 2 days, I think. So maybe some of you already tried to go inside, and I put the second one yesterday evening. So I will present them briefly. So the first one is about AST of arithmetical expressions. And you have a number of exercises to manage this structure per se. The point is that, okay, we can define the important notion, which is evaluation on this, but we can also perform some operation just on the trees. Okay, we will see that later. And the second file here is the basic idea is to be able to talk about a little bit more general arithmetical expressions. So these ones are very simple, only 3 constructors: constant, plus, multiplication. Okay, multiplication here. Then we will add other operations, such as subtraction. But okay, this is not that important. The important thing is that we also want to add a notion of variable. Be careful, a variable in the sense of imperative languages. Okay, here we want to. My aim at the end is to introduce a very small language called while, where we have basic loops and so on, and we have assignments. So we will talk within a language which is only made of pure expressions, like functional language. We will talk about a language which is an imperative language, but it is just a mathematical model. So anyway, as soon as we introduce an additional, or maybe it is somewhere in, yes, it is here. Okay, so you see the difference. So we have constants, we have plus, multiplication and subtraction, but also we have a constructor for so-called variables. And variables will be, okay, I will explain why we have a NAT here. And the point is that when you want to talk about the semantics of an expression which has variables, then you need to add something which we call a state. Okay, and this state will be represented by a list. So we need to have to be familiar with lists and natural numbers. So this file actually starts with the list and natural numbers. Okay, just to have the basic material, and then we can go on and consider more general arithmetical expressions. Okay, so basically these 2 files are technically rather simple. Okay, all you have to know are the most basic things I explained yesterday and Monday. Okay, so the theoretical background I started to explain will be useful. For instance, if you do something and you get a strange message, maybe I have to understand a little bit more on what is behind. Okay, but basically this is just programming. Okay, just recursive programming on trees. Okay, so I will go in the first file with you and maybe start to explain some solutions. Okay, not everything, because you have, it's better that you try by yourself, and then if something is somewhat difficult or whatever, or you have question because okay, you succeeded but you find that it is strange for some reason, so it's better that you try by yourself and give me your feedback. Okay, so okay, so let us start from the beginning. Okay, I think that this kind of tree is okay, is very simple. So at the moment, I don't care about NAT. We just have to know that the natural numbers you have in mind are there, and that we have some operations, that's the operations you expect. At the moment, we don't need to to go into the detail of this operation because it's very simple and somewhat boring. It's much more interesting to study this structure. Okay, so we just admit at the moment that not are there with the operations, and in the next file, we will be secured by the fact that it is actually some simple programming. Okay. So, I think you get the idea. This is just some examples which can be used later to make some tests. Okay. So, for instance, this one. So sorry, I have to start coq. Okay. Bon, maybe you want to see what happens. Okay. So 1 plus 2 3 times. Okay, so nothing difficult. So maybe the first one should be, so it is an addition first on 1 and 2. Okay. So there is only one pitfall here. You cannot say plus. I will not use the whiteboard, but you cannot. What you draw usually is without. We just put a number here, but actually you cannot say this. Okay, let us try. If I say this, and I want to make a multiplication, so I have to add a mu like this, and a 3. Okay. If you write that, of course, it doesn't work. Do you see why? So the reason, so if you don't see anyway, let us try. Coq will tell you that he is not happy. So it says that, the term 1 has type not, while it is expected to have type. Can you can you guess the rest of the sentence? I hope. Okay. So I copy paste here. So it's not what it is expected to have AXP. Okay. So here I put a 1, but it should be not a 1 alone. It should be an AEXP. So I have to make an AST from a NAT. How could I do that? Okay, right. So I have to put a hat on top of 1, saying that, it is, I make an AST from a NAT. So it becomes a little bit heavier. But it makes things very, maybe you have to type a little bit more, but so at least it is clean. Okay, so I expect that now it's okay. So for the second one, it will be the same. You just have to exchange what the plus and the these two things. Okay, so now the most basic semantics we provide in general are what we call functional semantics. It is the easiest to use. So whenever you can use functional semantics, use it, because if it is just a function, you gain something, that is, you can compute it very easily. And we learned yesterday that computation is something which is very interesting in proof assistance based on type theory like Coq. Okay, so it's good to use functional semantics. I mean, using the functions, the functional programs that we have seen. Okay, so any AC will be interpreted by a mathematical function, or more precisely by a computational function, I should say. Is more precise than, but no, because mathematical is a little bit Okay, it's more than that. A mathematical function just means a kind of relation which happens to be deterministic. It is more precise. It is something which is computed. So we like this because we are programmers. Okay, so we use the functions of the Coq language because these programs also have good properties. They have good mathematical properties. They are pure functions. Okay. So we call this function eval, not semantics. We call it eval because it is an evaluation. And we will use the operation called named plus and star of the standard library. So okay, so if I try this, okay, it works. But okay, so this is just in order for my file to be accepted by Caucasus, but of course this fixed point is wrong. So I have to put here the right material. So I said that for instance, okay, so I see that my function takes an AST and returns a NAT. So you see that for instance, this constant, this expression, this AST, okay, so that's type AEXP, but I return just the N which is inside. So that's simple. So now let us consider another case. I will leave that case. I should, because this way I can program step by step. There's another way of programming step by step. So the next constructor is APL. So you remember. So I write here a pattern. So here I had a pattern, constant of something. Now I have another pattern, say APL of an expression A1 and sorry, A1 and another one A2. Okay, so here I have two AST. So if it works, I will. What do I return? Merge. Okay, so I will evaluate A1. Is this what you mean? So anyway, so I have to evaluate A1. Okay. And I have also to evaluate A2 and A2. Okay, so I call my recursive function, okay, on the two subparts, on the two subtrees, okay, and when it's finished, I add the results. Okay, this is just written in the usual way. Okay, so this is the plus is just the function from NAT to NAT to NAT, which takes two natural numbers and returns the natural numbers addition. Okay, so if you want to be more clear, I can put the parenthesis like this, but anyway, okay, so you see, because in functional languages, function application is the most has the highest precedence. Okay, so I can check. Okay, this is still wrong because multiplication is not done. So you see, if I eval compute eval say expression 1, what should I get with the definition? Oh, let's try. Yes, 0. Yes, 0, because of course here, so you can see that here in the other cases I get a 0, and I precisely have this case here, which is not how to say explicitly taken into account in my current function. It is not taken into account, so the multiplication will return a 0. Okay, just by use of this clause. So of course, it is not what I want. What I really want is to finish my function. So I will add the last one. So I say if I have the constructor for multiplication applied to two subtrees, then okay, I make the same operation. Agreed? Oh, but no, because I expect a multiplication to be performed here. If I put an addition, so it is not because I write a functional program that it is correct. Okay, so this is why usually, if I make a copy paste too quickly, so or if I make typing mistakes, my program could be stupid like this. Okay. So okay, well, so let us put the right function now. I can leave that, I think. Maybe, I'm not sure that Coq. Yes, Coq. Coq consider this as an error because all the three patterns here, this one, and this one, together cover all cases. So this one could be considered as redundant. We could leave it after all, but okay, it is a little bit misleading. So Coq, the feedback of Coq says, okay, please remove this useless pattern. Okay, this is the answer we have here. Okay, so I remove this last pattern. So you see that I have the three basic patterns corresponding to the inductive definition of AXP. The second thing to see is that all recursive calls are performed on subtrees of the input. I have an input A, and whenever I have a recursive call, say here or there, for instance, I have 4 recursive calls, each time it is on a subtree of A. For instance, here AU2 here is a subtree of A because A is all this. Okay? So as it is a subtree, the recursive call will not, you have no risk of a loop forever. Okay? Okay, this is, okay, we'll come back to this in the theoretical part of the lecture later. Okay, now, if I compute my expression, this one, so I expect to have, so plus 1, 2, it should be 3. 3 times 3, I expect to get a 9. Yes, okay. So something else you can do is the following. Here, I'm just able to compute and see what happens. And okay, then I have to think a little bit. But another possibility should be, okay, I want to check that the expected value is 9 because, for instance, in the situation before, I put a plus here, okay? So I will get something. I will get a 6 maybe. Yes, it is not what is expected because in advance here I computed in my head. I saw that it should be a 9. So I can here check. I mean compute and see it is different, or I could do better. I could state a lemma. Okay, I could say, for instance, example val1, something like this. Say that, so I expect the previous result to be equal to 9. Okay. So this is a good way to okay. It is the basic way of making of simulating what you do in usual programming, making tests or assertions. Okay, so you say what you expect, so you test and you have a, but it's a little better. You have a theorem. Okay, so now let us compute. Sorry. Okay, proof. Okay, CBN for instance. Let us try reflexivity. After all, unable to. Okay, so this is the answer when you try to say that two things which are not the same should be the same. Okay, so I am wrong here. So at the moment, I just put an unlimited, or I expect a QED actually, but I am not able to to go, okay, to progress in my script. So let us think a little bit and say, oh, here it is wrong. I should put a star. Okay. Now I compute. 9. Okay. Looks better. Proof CBN 9 to. Okay. I am happy. Okay. So some basic ideas on how to check that what you are doing is good. Okay, so this is what I did. I used compute. I could say also eval CBN, etc. Okay. Okay, so if I want to respect what is the little exercise, I put it here. Okay, so now, okay, so this is the very basics. We have a type. So I finished actually. I finished the first part of my lecture. I defined AST for expressions. Then I define the semantics. So, okay, that's all. That's finished. But now I can consider other possibilities. I could, for instance, compute other things on the trees. And I think that at some point I will try also to consider a kind of optimization. So it's a very small compilation problem that I consider. So we'll see that later. Number of leaves. Okay, what is it? What is that? Okay, so I want to compute the number of leaves. So the leaves are the CST at the end. Okay. So, okay, it's up to you how to compute this one. So, of course, this is not the answer. So I have to, okay. We will use this pattern. Okay. Okay, so copy paste, and I basically this one should be useless. Okay, but I have to put the right thing, of course. So oh, sorry, I am not at the right place. Okay, so okay, so this one it is for later. Okay, this is the right place. Okay, so number of leaves. So okay, so here, how many leaves do I have in that case? Okay, so it is one leaf. Okay. Now, how many leaves do I have? Okay, okay. I said that eval is wrong. Of course, it should be. I will replace eval by. I will replace eval by number of leaves. Okay. Okay, so I have one leaf here. Suppose that the number of leaves of A1 is some number and the number of the leaves of E2 is some other number. What is the number of leaves of the whole? Well, it's the sum again. And what is the number of leaves for this one? It's also the sum, by the way. So my wrong function of first was actually right if I compute something else. Okay. So okay, just counting. Okay. So okay, again I could make some tests. We'll not do that now. It's up to you. So now another okay, little typo here. Reasoning. I'm not sure there were only one n. Okay. Some function defined as follows. So if the AST represents a constant, okay, we return this time. Okay, the idea is that we will return a new AST. The previous functions returned natural numbers. Now we will return an AST. Okay, so okay, I will change and I will replace eval by categorize. But okay, I have to find the the right thing somewhere. Okay. And I am just preparing the solution. Okay. So we say that in this case, we return the AST of the constant one. So we write it. Well, yeah, it is as said, it is a constant one. Okay. Now, if it is an addition, I just say it is a constant 2. Okay, so there is no fixed point. Okay, by the way, it is a definition. So you see there is no recursive call. So I just say it is a constant 2. And for the third, it is a constant 3. Okay, so actually it is okay. So maybe it's nicer to show this way. Okay, just presentation. Okay, this is my function. So what do I want now? Proves that the result, of the much French here, of the previous function returns returns an AST of size 1 in the sense of number of leaves. Okay, so the idea is that okay, I take an AST, I compute characterize on it. Okay, and I just want to check that I will get an AST of size 1. Okay, so I take an AST and it has the size 1. Oh yes, okay, that's right. I was wondering if the question was as expected. Okay, so let us put that on the top. On the top, okay. Sorry. This one, I want to see this one. Oh, penable. Okay. So what I want to show is here. So number of leaves and categorize, okay? We say that for all A, the number of leaves of the result of the previous function returns always 1. Okay? So a very simple theorem. Okay, and here it just it is just a reasoning by case. So do you remember what is the first tactic to be used? Sorry, I need to put this somewhere else. Okay, so this is my goal here, which is a four-old goal, a four-old A. What is the first thing to do? Yes? Intro? Okay. So let us say, okay, let us take some arbitrary tree called A, okay, like arithmetic expression. Okay. And now let us compute this. Let us try to prove this. We could try a CBN, but no progress. Why? No progress because A is unknown, so categories cannot perform any computation. Okay. So okay, so there is no point to keep it. So what do we have to do? Yes, we have to consider the 3 different cases of an AEXP of A. Okay, so destruct A. So we have 3 cases. So the right way to write destruct is to okay. So in the first case, A should be made of a number. In the second case, you should have a first subtree, and a second subtree, and same for the third case. Somewhat explicit. Okay, so I have my 3 cases, and I get 3 goals. Okay, and on each of them now we can perform the computation. Okay, because now we see that category. Of course, this tree is not completely known. Be aware of that. OCaml is, for instance, a real programming language. I mean, like OCaml. Okay, it does not make sense to ask the question to OCaml because OCaml only want completely what we call closed trees, closed value, a value which is only made of constants and constructors. But for mathematical proof assistant, it makes sense. So this is why the evaluation mechanism of Coq is more advanced than the one of OCaml. So here, Coq is able to say, okay, yes, I don't know n, but it is enough for me because I already just from knowing that it is a constructor of something, this constructor here, so category is here, I know that CST of anything returns something, so I can start the computation in some sense, okay? So this is the power of CBN. So CBN will, okay, we will perform the computation. So categorize of CST of n will return. Okay, maybe I will do that step by step. I will only reduce categorize. Okay, so we will see that that here we get a CST1 instead of CSTN. Okay, this is this computation here, and now I can reduce NBL. Okay, oh sorry. Okay, and we see that NBL of CST something, NBL of CST something will return 1. Okay, and then, okay, so we see here all the steps in small details. Okay, for the second one, I will be a little bit faster. I could say, for instance, sorry, I could say, okay, reduce as much as possible for all functions which are there. For instance, reduce for categorize and then reduce for NBL. So okay, I could say this explicitly like this. So CBN of categorize, sorry, and NBL. Okay, so I do the two steps together. Okay, so I still explicit, but I ask to perform the two reductions at once. Okay. Okay, so this is very similar to the previous one. I could also say, okay, just CVN. Okay, I'm lazy, and that's the same. Okay. I can even not perform the CBN at all. Or actually, if I write reflexivity, it works. Okay, so this is for a subtle reason. Okay, I started to explain that yesterday. Maybe I will go back to this later. But the point is that in practice, if by computation, this is important. If the two things which are here and there by computation provide the same thing. So on the right, there is nothing to compute, but here we can compute by CBN, for instance, and it provides the one. So actually, this and 1 represents the same thing for Coq at this level. Okay, so just reflexivity will works in the place. Of course, at the beginning, it's better for you to perform the CBN because even when you are professional, it's better sometimes to be more explicit to follow what happens. Okay, so now I remove my admitted. I can send QED. I am happy. And if I forgot this, Coq will complain. Okay. Okay, so success. Now, what is the next exercise? Oh, okay, something similar to NBL, but with a different counting algorithm. For this one, I will not count the number of leaves, but the number of nodes. Okay, so it's very similar to the previous one here. Okay, and make some replacement. Okay, so how many leaves here? How many leaves? Sorry. How many nodes? I mean things like APL or mu. How many binary operations in CST of n? 0. Okay. How many? Number of nodes for this case? Oh, okay. So I have to replace NBL by NBO. Oh. No. Okay. Reduce by hands. It's that long. Okay. So assume that this one has some number, say n1 nodes, and this one has n2 nodes. Okay, this number. What will be the number of nodes, of binary nodes for this one? So I have to put, okay, it is not only the sum, because you see, if it is only the sum, I will get always a 0. So I have to add 1 here. Okay. So my preferred way to add 1, so we could say 1 plus blah, 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 or this plus that plus 1. My preferred way is to put the 1 at the middle. Okay, because I follow some right to left order. This number plus 1 plus this, the number corresponding to A1, then plus 1 corresponding to the APL, which is in the middle. If you roll the tree, this one is in the middle. And so on. Okay, and actually it is not just a matter of taste, it is because it makes some proofs simpler later. We will see that later. We can always deal with the other. Actually, I don't like too much. Okay, we will see. I don't like this way of writing the theorem. Okay. So now there is a funny relation between NBO and NBL, which is the following. It is that NBL, the number of leaves, is equal to the number of operations plus 1. So whatever your tree could be balanced or not at all. Okay. Anyway, you have this relation. And just imagine, if you think in your head of some example, okay, let us take the examples we had at the beginning, this one, for instance. Okay, it is easier to see here. Here you see that the number of leads is 3 and the number of operators is 2. Just a simple example. But you can see you can have something completely unbalanced and any size. You have this funny relation. Okay. So it is typically something that will be proved this time not by case but by induction, because the property will be propagated from the bottom to the root. Okay. So some tricks which can be useful, because here we need to reason on additions. Okay. So later we will prove this basic theorem. There is nothing magic here. But at the moment, we are interested in the important theorem, not on little things on numbers. Okay, so the important theorems. Okay, so we will use what is already available in the library, in the Coq library. Okay, so Coq says something. I don't care about that. Import NAT. Okay, this is a way to to have a better view on what happened. So here we suggest what is the useful theorem to be used it is called add ASOC, which says that the operation, the addition is associative. It is what you expect. Okay, I will copy paste. Okay, oh no, I will not copy paste. You can see that. So for L and M P, okay, N plus M plus P is equal to N plus M plus P. You understand here that Koch has an implicit grouping of things on addition, which is that is N plus M is computed first like this. It is like at the school when you have a series of additions. Usually you add from the left to the right. It is just the normal convention. But okay. So this is a basic theorem. Very difficult to prove. We will just use it at the moment. Okay. So okay. Actually, I like so much. Okay, I will see if it works. Okay. Yes, I see you. Okay. Let us leave it as it is here. Okay. So the proof will be performed by induction on A. So as usual, it is a for all. I'll introduce it. And now I will perform my induction on all the possible shapes of A. So 3 possibilities, the constant of n, an addition operator with 2 subtrees, A1 and A2, and each of them comes with its own, with its own induction hypothesis. Okay, so here we assume that the theorem has been proved on the 2 subtrees of the big tree. Okay, and same thing for the multiplication. Okay, so now we have to finish the proof by considering each goal separately. So first sub goal. Okay, so okay, what could I do here? So I have, what you have to see is that you have computable functions, NBL and NBO. So I have functions that can be that could be computed and can actually be computed because they are applied to something which starts to be known. Okay, I already know the starting of the shape of here, so I can compute. Okay, so I will compute NBO and compute NBL. So in my head, I know that this number should be 1 and that this number should be 0. And I will get 1 should be equal to 0 plus 1. Okay. Okay, let us do that. Okay, because if I say CBN too early, okay, so NBL and NBO, that's all. We get this one. And again, it can be computed because plus is a function defined in the library. Okay, so I don't know the definition, but okay, I know. So I finish the whole computation, CBN of the plus, okay, and reflexivity. Okay, let us continue. Second case, here I have arbitrary sub-expressions A1 and A2 coming, each of them comes with its own induction hypothesis. And okay, again, I need to prove the theorem for the whole, okay, for the whole tree made of A1 and A2. So once again, I will perform a CBN. So let us do it like this. Okay. Ah, I have to go on this. Okay, here. Can you see? Okay. Okay, so you see that, remember, this means NBO applied to A1. We have implicitly parentheses here, okay? Because once again, function application is has highest precedence. The same here, okay? So we have one number plus 1. This is the one I had in the middle here, plus a number plus 1. Okay. Okay. So, for instance, okay, I'm not sure that I can. Yes, here I have NBL of A1, so I could rewrite here. Okay. Okay. Oh, let us use our induction hypothesis. So hrec for A1. Okay. Okay, it starts to be okay. Okay, let us continue. Same thing. So first one, second one. Okay. It looks very similar, but here we have parentheses. So if I try reflexivity, unfortunately, I'm afraid that boom. Okay, Coq. Okay, complains because it looks similar, and you could be frustrated because you learn from at the school that it should be the same, but no, it's not that simple. It is the same, but not by computation. Okay, the meaning of that, it is not equal by computation. It is equal because of a theorem. It has been proved by induction, actually. So it is not something that simple, okay? So it is exactly the place where we need to use associativity. Okay. So reflexivity is too early. So let us again check associativity to understand how I can use it, because here I don't know. I cannot say just apply ASOC blindly. So I need to remember what states exactly associativity. Associativity states that this plus that with parenthesis is equal to that. Okay, I have to understand exactly what it is. Okay, it actually is some number. Okay, these two are together. Okay. Okay, and this also is together. I'm curious, but I guess that okay, because basically it is an equality. Okay, it is a generalized equality. Okay. Okay, I will do something I learned yesterday. I learned this. Okay, I wanted to go back to this in the theoretical part, but okay, let us explain it very basically. Okay, I will proceed step by step. Again, I check add a soc. So you know that add a soc actually is a function from n MIP. So I can apply check a soc to a suitable number. So I think that the suitable number is this one, NBO of A1. Okay, so you see the result is the result of this function ADASOC applied to NBO1 is for all NP, NBO A1 plus M plus P is equal to NBO A1. Okay, it is not what I want. I want actually NBO of A1 plus 1. Okay, so let us check this one. Yes, it looks okay. It looks closer to what to my goal. Okay, you see, NBO A1 plus 1 plus something plus this one. Okay, so this looks like I should take for M. For M, I should take NBO of A2, and for P, I should take 1. Okay, so let us. So again, the same. And now I will add another parameter, which is NBO of A2. Okay, and let us guess that the third is this one. Okay, so I apply my function ADASOC to these three values. Oh, okay, this is the functional view, but as a logician, you would just say, okay, I take an instance in some sense of the general theorem by taking for n and p respectively the three values explained here. Okay, so I apply my theorem on these three values successively. Okay, but applying has the same meaning in functional programming. Okay, so okay, so let us see, and what I have is exactly what I have. So you see that actually, even if ASOC concludes the conclusion of ASOC is an equality, usually using an equality is performed by rewrite. In this case, okay, I could use a rewrite, but I also could just say, okay, this is just okay. This is, by just using this expression, I have a proof of this goal. Okay, so okay, I will just copy paste, and instead of check, say, okay, it is exactly what I want. Exact. I think parentheses are needed here. Okay. Okay. Okay, here I have, okay, in real life, we don't do like this, but here I showed, I wanted to show the very detailed mechanism which is performed. Okay. So for the second one, I will, okay, by chance, I have another goal here to see how to do the same thing more quickly. I could say, actually, okay, so anyway, at the beginning is the same. We will do the CBN computation. Really, it has a same. So I am in exactly the same situation, and instead of saying check, instead of okay, instead of at the end, okay, I could do that. Okay, so let us try. It will work. Okay, but if you think it is a little bit boring to provide by yourself all the values, you can just say, okay, try to apply ASOC, the theorem. Please, Coq, apply your theorem and try to find by yourself the values. Maybe Coq will be able to do that. Maybe not, but we can try. Okay. So Coq is able to recognize the three specific arguments which are suitable to finish the proof. Okay. But basically, it is exactly the same proof as before. And okay, no reflexivity actually. Okay. So I could also another. Okay, so it is one possibility. Another one. Okay, I will undo what I did. Okay, I could try the rewrite actually. If I rewrite ADASOC to see what happens. So basically, I think that the left-hand side here will be recognized. Okay, once again, it is actually a rewrite of ADASOC applied to blah, blah, blah. Okay, actually, but Coq will say we have some advanced usage of rewrite. It is a rewrite to the theorem applied to suitable arguments. We have seen yesterday that actually sometimes we need to be more precise on the argument. But I think that in that case, Coq will recognize what can be done. Okay, so Coq will rewrite this part and replace it by okay, the right-hand side of ADASOC. So let us see what it provides. So you get on the left-hand side something which has been rewritten, and on the left, yes, and on the right, the same. Okay, nothing to okay. But now I see that I have exactly the same expression on the left and on the right of the equal sign. So I can do reflexivity. So you see that actually the apply is more efficient. In only one step, I am finished. Here, I can also use the rewrite, but then I need an additional reflexivity. Okay, so it depends on your choice. Both are possible. Okay, so I think that here, Okay, and then we can happily, okay, don't forget, because, okay, admitted works. But if, so it works, I mean, you can continue the script. But it is bad to leave unadmitted, because the meaning of admitted is actually that you tried to finish a proof and you were not able to finish the proof. So sometimes it is very useful because, okay, you have in your head the architecture of a big proof, and you think that you have first step, second step. Okay, so you design a number of lemmas. You think that they should be provable, and you can start a little bit to see what happens, but you don't want to go into all the details. And then you are interested to see if you are able to prove this previous lemma, then would it be enough to prove the main theorem? So you admit your lemmas, and you think it will be for okay, for later. You postpone the proof, okay, but you can use them, okay. But so here I could be able to use this lemma, but actually it means that the work is not finished. So if you have a reviewer, because a script is supposed to be reviewed by a friend, by any reviewer, okay. So the first thing, or you could be asked to review a Coq script. The first thing you have to check is whether your colleague left some admitted in his script. If there is anything which is admitted, it means that the work is not finished. He can claim that he has a big theorem at the end, proving that n is different from np is different from p or whatever, okay? But if there is some admitted in the middle, and in that case, probably there is an admitted, you can say, oh, no, I don't believe that you proved the theorem, okay? So in that case, it's pity, because you actually finished the proof. So because actually you were able to finish. Okay, so okay, I will go here, Control C, Control Return. Okay. Okay, so what could be done now? Transform. Ah, yes. Okay, so the next one, okay, is the starting of something which will become more interesting. Okay, I will replace constants by 1 and replace all binary operators by a plus. Okay, so you see, somebody gave me an expression, and okay, I do this operation. Maybe this one. No, I think. What time is it? No. Okay. I think. Okay, we'll just present the exercise. I think you should do it by yourself. I will just correct it. I think there is nothing really new to show. This one. This is really an application exercise. So just look at the question. So you see that constants becomes only constant of 1, and multiplication are replaced by plus. Okay, I have okay. Okay, all the okay. This is a simple transformation. What I want to prove is that in that case, yes, that's funny actually. If I evaluate the transformation of A, I just get the number of leaves of A. Okay, yes, because all constants becomes 1. Okay, so I have ones at the end, at the leaves, and for the rest, okay, I just get okay, a plus. Okay, so actually, I think I could keep the operators. Basically, the important thing is that the constants have been replaced by 1. Ah, no, because I evaluate. Sorry, I evaluate. So yes, so even the multiplication has to be interpreted as a sum. Okay, okay. So okay, you can try by yourself. I think there is nothing difficult. It's just somewhat funny. Okay.
Now, the last one is a little bit more interesting from the point of view of possible applications. I want to optimize expressions. The idea is the following. I want, okay, so there are many kinds of optimization you can imagine, actually. Okay, imagine an expression. So here I will focus on only the zeros and even on zero on the left. So I say that, okay, whenever I find a zero on the left of the multiplication, the result should be zero, whatever the contents of the right expression. Each time I have zero times a big thing, the result is zero before computing it, okay? And each time I have a zero plus something, there is no need to compute the plus. I should just evaluate the right-hand side, okay? Of course, I could imagine further optimization. For instance, what happens when I have a one? What do I have when I have also a zero on the right, and so on, okay? So the example can be improved a lot, but I just want to show you the start of how to deal with that, okay? So the point is how to write the right function for doing that, because you want to perform the transformation everywhere in the tree. So you have a little bit, you have to think a little bit on the if you want to program this function. But I provide you a suitable solution. You need an auxiliary function. An auxiliary function, I call it simple zero, which performs the simplification only at the root. This is the first function. And then I will, okay, so the first function is simple zero. And you see that if I simplify this tree here, then I will just replace it by A2, okay? So again, it is a transformation on AST. Same thing for a null. If I have a null of a CST of zero, okay, I will replace it by the CST of zero. And you see, if you have a plus applied to a null with a zero, so recursively, you will improve the optimization. So it is necessary to repeat this operation. So at the moment, it is only at the root. Okay, and now, yes, and I say that simple zero of anything else returns the same thing. Okay, so I have a function which I can write. Okay, define with e like this. Okay, so let us do it. So match A with yes. So I use more advanced pattern matching than in the previous example. In the previous example, I just have CST, null, and add. Okay. Here I have a pattern matching which combines add with a CST. You see, so the proof will become more interesting. So the function is interesting. So let's write it. So when I find a pattern, an AST having this shape, add of CST of zero. So zero can be seen as a constant, okay? And A2, okay, in that case, I return A2. Actually, what I write here is just the same thing as is drawn before. Let me see. Yes, I return A2. Sorry? Yes, but it is necessary. You see.
Your constructor is well called add for API. Did you provide the definition of the AEST?
Yes. Actually, yes. Yeah, okay. But I think, okay. What is in comments is sometimes wrong because comments are not type checked.
Yeah.
Okay. So, okay. Thank you. So it is not add. It is now. It's called the APL. You are right. CST is correct. And here now is the right name now is a new. You are right. Anyway, here it would be caught at this point. I mean, if I try with the wrong names here. So if I put null, Yes, it was okay. So in that case, I will say I will return the constant 0. Okay, and in all the case, you see this is all the pattern matching of in all the case. I return A. Okay. So if I go here, okay, so complaints, and then we are, I should say what APL, by the way, it is like this, and here it should be A new. Okay, I hope that the rest is okay. Yes. Okay. So Coq is able to, type checking is able to catch typing mistakes as usual. Okay, so I have my basic simplification function which works only at the root. Now I want to I will repeat this operation recursively. Before doing that, I will prove a simple result on simple 0. Okay, which will be useful for in the sequel. So I want to prove that simple 0 preserves the semantics. Okay, so if simple 0 of something is equal to, I mean, the evaluation of the result of simple is the same as the result of the if I evaluate all. Okay, so it is what you expect. Okay, and the point is that in order to prove that, okay, think a little bit. Basically, if you only use what you learned until now here, you will have a boring proof, because basically this definition use some deep, not that deep, but a little bit deep pattern matching. Okay, not only one level but two levels of constructors. Okay, you see that on the drawing. Okay, so but for reasoning, you only know one trick: reasoning by case on only at one level. Okay, so you can do the proof. Actually, you can do the proof, but if you do that in the standard way, it will be a bit annoying, because you will have to consider two consecutive levels. So instead of 3 cases, maybe we'll have 9 cases, something like this. Okay, it's feasible, but it's just boring. Actually, what you can understand is that the proof of any proof on such a function, and this is a very important principle, proofs should follow the definition. Here I have a definition with 3 patterns, and I would like to have a proof which have exactly 3 shapes like this to consider. This is what I want to do. Okay, so this is really I mean using again the Curry-Howard correspondence we saw yesterday, a little bit more advanced level, but it is really the same idea. The proof should follow exactly this pattern here. This can be done, okay, and actually, with what we saw yesterday, so with my students in front, actually, what the material of this study was not presented. They are not able to use something we learned yesterday, which is just a tactic refine. The point is just using the refine tactic in proof mode, using exactly this pattern. So we will have a refine with a match. Then you will be able to make the proof without using anything new. In that case, what I proposed is to perform this refine here. So the refine is written here. You can see in this case. Okay, I will consider this case and then see what is the goal, the new sub goal. See the second pattern here, and we will see what is the circle in that case. And I want to see we have a joker here for representing the sub goal I will get. And in all other goals, I guess that actually for in all the goal, I keep the same A. So evaluating should return the same thing. So I expect that in all of the goal, the proof will be just by reflexivity. Okay. So there is one thing I did not show you maybe is that reflexivity inside Coq, it is represented by a proof tree, by a thing which is called EQRef or RefleQ. Okay, maybe EQRef. Okay. Just to check that I'm not wrong. I think this one is simpler. Oh no. Okay, maybe it is because something has been imported. So, okay, so Coq refused to. Okay, okay. So Coq improved, and so there are a number of things that we cannot see. Okay, so anyway, I expect that it is up to date. Let us see. At the moment, but it doesn't mean anything. Okay, so we will see if it works. Okay, so okay, the last thing to know is that Coq includes a complicated an additional mechanism to combine combine tactics. So I will not teach it here. The point that okay, just have an intuitive meaning of what it means. Here it is basically a refine with something which should, I hope, is still okay in the conversion of Coq on the goal. Okay, and basically we would just it just means okay, consider the two important case and okay and then we will see what we can do in that case, and in all the case reflexivity should work. Okay, so now we will see the lemmas which could be useful. Of course, yes, 0 plus n is equal to n. Okay, this is one of the basic lemma of the library. It is an exercise to be done later. The same for multiplication. For any number n, 0 times n is equal to 0. Okay. Okay, so remember that we have that in our pocket. Okay. And now let us prove the important thing with the important lemma, which is that eval of simple of A returns the eval of A. Okay, so the optimization is correct. Okay, so we introduce A as usual, and now instead of destruct A, which would be the standard way, we will use our tactic, which is called K simple. This one, okay, K simple 0. This is our own tactic. And I hope that I get exactly. Yes, it works. So the curve here still works. Okay, that's fine. Okay, so I have two sub goals. The first goal for the first pattern and the second goal for the second pattern. The first deep pattern. Okay, and okay, let us look. Okay. Okay. So eval simple 0, blah, blah, blah. Okay, now we can simplify this one. Yeah, you see that we have a complete pattern here which correspond to our function. So simple 0 should, to start the computation of this tree, okay, and return, I think it should return A2, if I am not wrong. Okay, yes, so we have A2. And here we also should okay, and we have this. Okay, so simple 0 has been performed, and now what about eval? So let us compute eval, and we get eval of A2 should be equal to 0 plus eval of A2. So in that case, we will remember this lemma. Okay, so you could do another way if you like, but okay, this one okay is possible. So we rewrite it or we apply it, I think. Or anyway, yes. Ah, yes, because it is on the opposite side. Okay. At 0L, rewrite, yes. If again, if I check this one, yes, 0 plus n is equal to n. Okay, but we want the equality in the reverse order. Okay, so we cannot apply the theorem. Okay, but we can rewrite. We can rewrite this 0 plus eval 2. Okay, once again, so rewrite. Once again, it is actually add 0L applied to, if we want to be very precise, to apply to eval A2. If you want to be very precise on what happens, and in that case, okay, you get eval 2, and then reflexivity works. Okay. Okay, so you can finish by yourself. Okay, so I do what I said before. I don't finish the proof. You will finish, but I will be able to use this theorem. But my file is not satisfactory. But I can progress. Okay, now let us use simple zero recursively. Okay, so this time yes.
For the L type, if I case simple zero,
Hmm?
You have 3 jokers after the double arrow.
Yes.
What do they mean?
What do you mean?
Yeah, the first joker, yeah. After the double arrow, yeah.
You mean
This one,
the joker here? Okay.
What's the meaning of this one? And also the third one, you have this EQ rep followed by this joker. And then what's the difference? No.
I will show you the direct way.
Okay,
yes,
fine.
I just copy.
Yeah.
Actually, I can completely copy paste because the A is the same argument. Okay.
Yeah, and then this is fine.
So it is exactly the refine you will learn yesterday. There is nothing new actually.
Yeah, I just wondering.
So now remember that refine, the argument of refine, is just a program to be completed. Okay, so it is a match A with, so you can recognize, okay, these 3 shapes exactly as in my okay, actually it is a copy paste of the definition of the function simple zero. Okay. Okay, so maybe it's better to write like this. Okay.
So when you leave the joker inside, that's the part of the proof.
Okay. Yes. So the only thing is that inside a refine you have a program, and in some places you have a hole, and the hole means, okay, at this part I want to complete. I need to complete the program. At this moment, it's not completed. Okay, and this part will be okay. We will be completed later, and it's just provides sub goals.
Yeah.
Okay, so here we have one sub goal. Here I have another sub goal, but here it is okay. This is a little bit annoying here, but actually, this is another. It is another. Underscore here. This actually this is a parameter of EQREFL, which is enough. Okay, actually it is because this EQREFL has an implicit parameter.
One.
Oh,
okay.
but there's something strange because okay.
Let's say control to first. After one, double one.
The problem is that so I am in a state, in a Coq state, I mean, where libraries have been imported, and importing these libraries make the basic equality definition a little bit different. So, I was not aware of this because, for some reason, I guess that the Coq people had good reason to make things a little bit more abstract about equality. And one of the effects of that is that my usual reflex does not work. So, we had to change a bit. So we have something complicated. Relation classes dot reflexive. I don't know. So the simple equality becomes something more abstract for some reason. So this is why we have this graph here.
Can we put another one? Yeah. So that's one.
Okay. He says that eqref of x of type x equal to x cannot be blah blah blah. Okay, there is a possibility is to put this. No, still not. No. Okay, what we can do is to type show proof. You will see exactly what Coq understood. So it's a little bit complicated to understand. So this is just for Professor Deng and myself. Okay. So we see. We see. Okay. What do we see? Actually, yes, because this deep pattern matching has been compiled into two successive pattern matching. The first one here, the second one here, even three. Pattern matching. Okay. So we have a constant. Anyway, constant of something is one of the cases. So it is at the top. So we can see that. eqref. Okay. So eqref expects exactly. I understand now. Okay. So eqref expects exactly one argument, which is the left-hand side of the equality. Okay. And actually, there is another parameter which is not shown here, which is the type of this thing. So actually, it is eqref applied to AST, to IX, then applied to this one. So this is a committed, but the first one is implicit. Okay. I wonder if A could work. No, but maybe if I say A prime and A prime, I try, I'm not sure. No. Because it is eval. Maybe it is this one. Yes. Okay, so here we have something which is more explicit, but a little bit complicated to understand for the general audience. Okay, but for advanced users, you can see that basically there is this LTAC with something a little bit of magic with this underscore, which has to be understood in a different way than this underscore there. Okay, this is not the same. This one means please find the you have some work to finish, but this one means actually Coq will be able. So it is a little problem with Coq. Sometimes underscore means a different thing, and here it is a third meaning, but here you understand it is just the general. It is the joker for pattern matching. Okay. So don't be lost by this. Okay, for the basic students in we just provide them this tactic, and they are just supposed to write case simple 0 of A. Okay, it does the work, and intuitively you understand what happens. Okay, now if you want to look into the details, it's not that complicated. Okay, it's not that complicated after all, but okay. Okay, so we can leave that here. Okay, so now blah blah blah. Okay, so you will finish the proof. Okay, so now okay, so I should undo one. Okay. Okay, so now let us interesting function, the complete optimization function here. So of course it is not return 0. It would be. Okay. Okay. It's really long. Okay, I agree. But the file is almost finished. That's the good news. Has this type. X is equal to X. Okay, something which have and okay, where it's with some okay, some mechanism called essential variables. Okay, whatever. Okay. But it is clear. You see, if you require import the arithmetic library, still the same.
Yeah.
But I did an import NUT. Okay, for some reason, in order to have easier naming of the theorems, and then the QRF became something complicated. So, okay, so maybe it's better not to import NUT and to call the and call the theorems. Okay, it depends on what you want. Maybe you could have good reasons to have this abstract view on equality. Okay. Yes, I think this is maybe some people want to perform reasoning by rewrite and rewrite, and I know that there is some kind of uniform way of using rewriting, but using more advanced mechanism based on because if you are in a type, in a class, I mean a set, a combination of a type and operations which are congruent in some sense, then you want to just say rewrite, but actually it is not the equality, it is just an equivalence, which is you are supposed to use only the operations of the class. Okay, so in math you have very often this kind of situation, so it corresponds to different use. Okay, so anyway, here we have the explanation. Okay, so let us finish this file. Almost finished because I left some holes. So we want to define recursively a simplification function. I call it a simple rec. So of course I will okay, I will make a copy paste of the match. No, no, not simple 0. It is something special. Let us take an example. Well, this one, for instance. Okay. Okay, so okay, I'll remove. Okay, what should I have here? So I just want to repeat the recursive, the call to a simple 0. So in that case, I have nothing special to simplify. constant, it is just the same. Okay. Yes, and the idea now is that I will perform the simplification of A1. Okay, let us write it. Maybe I need some room. Okay, simplification. I will simplify A1. Okay. Okay, let us put parentheses for clarity. I will do the same on A2. Or maybe one line will be enough. Okay. Okay, the idea is that then I could just add the original constructor. At the moment, no simplification has been performed. Okay, I just say that, okay, I simplify on the left and simplify on the right. I put my operator on the top. And now I will call simplify 0. I think this one is correct. Do you agree? Okay. You see that here, recursively, I will get, okay, I will remove all the zeros in A1. I will remove all the zero in A2, but still, for instance, I could get here a constant of 0, okay? Because, okay, for instance, if A1 is just constant of 0, okay, I will get constant of 0 here, okay? Same thing for here, I will get something. But now I have a plus of constant of 0. I have an opportunity to simplify at the root. Okay, so the idea is that you simplify the tree, you simplify this whole thing. You make the recursive work on this full tree on A1 and A2. Okay, you have still your AP at the root, and now you call simple 0 on the root. Okay, and then I think you just have the same thing here, except that you have a multiplication. Okay, and okay, I think it's a good function. Okay, and now just prove that the simplification yields the same result. Okay, but actually here the proof is very simple. Because why it is simple? The proof is simple because you see that it is just a definition, a recursive definition. I assume that this one will be correct. This one will return a correct result. And then at the end, applying simple 0 on APL of the on two correct things should return something correct because simple 0 is supposed to behave correctly. Okay, so I think that the proof here is very simple. So we can just start, okay, to see what happens. So intro A with a lowercase letter. Okay. Then induction as usual, induction on A with, okay, so I will not write the name of the constructors. So the first constructor provides an N. The second constructor provides a subtree A1 with its hypothesis. Okay, I will call okay. I use the French. I think I said the induction hypothesis. I'll call them H. Okay, because in French we say hypothèse de récurrence. Induction is okay. So I should the English meaning should be induction hypothesis. Okay, so maybe I will translate these names. Okay, they are just names, of course, but it is better when they are intuitive. So, okay, here I will call it induction hypothesis on H1 and induction hypothesis on H2, on A2, sorry. And the last case has exactly the same shape, but it is for the null constructor. Okay, so in each case, the only thing to do is to actually to perform the computation, because as usual, you have this fixed point applied to specific shapes. So we already have information on what is this tree A, and so the computation can be started, and just performing CBN on this one. Okay, let's be short. We'll provide CS. Okay, okay. We have CBN of CST, but also the eval of the result. So I will have the eval of CSTN and the eval of CST. Actually, I don't need to perform the CBN on everything. I think CBN on simple rate is enough. I don't need to. Okay, I am more precise, but actually, here is already enough to conclude. I don't need to. I will get n is equal to n, but even before computing, I already see that this and that are the same. So even no need to compute what is eval. Okay, so reflexivity. Okay. Otherwise, it is not that. Okay. So last second sub goal. Yes, so I here see something dirty here. This is because I forgot something. So I have A1, its induction hypothesis, but I forgot to say that I have A2. So if you see bad names, look at what you wrote. Maybe you forget something, as I did right now. Okay, so let us go back here. Okay, now it looks better. I have my two subtrees with the two induction hypotheses. Once again, maybe it's good to be careful and to just perform the CBN at this level. Okay. And now I have an equality which talks about simple zero. This is, I think, maybe it is not necessary to once again to try to evaluate. I will see later. I just see that I have a simple zero of something. Okay, and I know I have a theorem about simple zero. I have a theorem which says that simple zero of what does it say, my theorem? Or maybe I need to go further. My theorem says that the eval of simple zero is equal to the eval. The eval, yes, that's good. I have the eval of simple zero. Well, the eval of simple zero of something complicated, whatever it is, should be the eval of this thing. So I think yes, no need to. Yes, CBN maybe is misleading. Okay, I think that rewrite of simple zero. Okay, actually, I should provide the argument of simple zero, but I have to copy paste all this. Okay, I could do that, but okay, I'm too lazy now, so I will do that and. Yes, it is not. Sorry, sorry. Simple zero is not the theorem. Simple zero is a function. It is my theorem is called eval simple zero. Sorry. Okay, so this is a rewrite the eval simple zero. Eval simple zero. Okay. Now I think it should. Okay. So I have eval. Let's see, eval of this should be equal to that. Okay, so yes, okay. Here I think I need to, yes, I need to compute eval in order to see that eval of APL something is if the sum of evals of this. Yes, I need to compute eval now. Okay, you see why? I have eval of APL and two expressions, but I know I have nothing. I have nothing on this expression alone. What I have is eval of that, and I have not eval of that. I have this thing is below an APL, so I cannot progress here. Okay. If I try, by the way, let us try rewrite, for instance, of the induction hypothesis on A1, and Koch will complain that there is nothing to rewrite. Okay, for no subterm matching eval of, there is no eval of simple rec here. But now, if I compute a little bit about eval, it will be possible. So fail. But now, let us CBN eval. Now I have the eval of this. Okay, so I can use my induction hypothesis. I will get eval A1 and same for about A2, and I will be done. Okay. So you can finish by yourself. And the last case is exactly along the same line. Maybe interesting because I mean mistakes can be interesting. So I don't know if it is a mistake to try a big CBN here. So I say try to simplify as much as possible. Maybe it will be a good thing, but maybe not, because maybe it's more careful to have an opportunity to use to use this theorem. And maybe if I simplify too much, maybe I will be in a situation which is too simple in some sense for this one. I don't know, so I have to try. Let us simplify. Okay, I get something terrible here. You see, I compute too much, and then I get something I don't know. I don't see how to use it. So the reason, what is the reason? The reason is that I have simple rec called simple zero, and all of them have enough information to continue the computation. So it computes too much. It just computes too much, and then I have no longer opportunities to use my previous theorem. So you see that sometimes it's good to be lazy. Okay, CBN. Okay, but here CBN is too greedy. I don't know how to say, and yes. Yes, I have really. Yes, I think from this situation, it's difficult to finish. So so once again, it is a good opportunity to say, think about what you are doing. How would you like to finish your proof? Actually, clearly, you want to finish your proof by using theorem simple zero, because intuitively you see that this function simple rec use simple zero, and of course you see that this theorem here, the theorem just before eval simple zero, this is the important theorem. It says that at each step, okay, evaluation returns the same thing. But as the simple zero function is a little bit clever, it makes pattern matching at two levels. Okay, so the computation could be too greedy, and okay. So here it's good to. Oh, sorry. not to be too fast. So just one level of simple rec. So simple zero is still visible here. Sorry, and I would like to keep. Okay, to have this one. Okay, so we can see if I simplify simple zero here, I think it's possible, but I will be lost. Yes, again. So I get more or less, or exactly maybe the same situation as before. Okay, so it is good to simplify the fixed point, but it is bad to simplify simple zero. So the reason is that simple zero does some complicated pattern matching, and the right way to deal with this pattern matching is to use this theorem, because this theorem actually performs the right pattern matching for reasoning about simple zero. Okay, so you see that the reasoning about functions is exactly following how the functions are written. So if I just make CBN with blindly, okay, so simple zero will work too much, whereas I should actually, in some sense, use this pattern matching. But okay, in order to do that, the right thing to do is to not to go slower, to be slower, and okay, so that I have an opportunity to see eval of simple zero and not simplify simple zero. So simplification is good, but sometimes not. To this one. Now it is the right thing to do is this one. Now I have to compute. Okay. Here I could try CBN blindly, I think. Let us try CBN. Yes, CBN, and actually they are equivalent, but because at this stage, the only function. Oh no, we have two functions. We have simple rec and you have eval. But simple rec is applied to a variable, so there is nothing to compute on a variable. So no room at this stage for additional computation. But eval has room. Eval has an opportunity to reduce here and there. So there are two opportunities to reduce eval, and both of them, okay, so CBN of eval and CBN will be equivalent. Okay, so let us finish on this file. So I think you should be able to try by yourself, and if you have questions, as usual, don't hesitate to write me, because I will not put the solution on the web. Better for you to try by yourself. Now, maybe, okay, I still have less between half and 1 hour. I would spend some time on the theoretical part, but I don't need so much time. Okay, let us see if. Okay, let us go to this file. Okay, so this is what I announced. We will the final idea will be to work with more advanced arithmetical expressions. So arithmetical expressions which include variables of an imperative language. Okay. So, but before that, I need to be able to formalize a notion of state, and I will also need more. Okay, to understand a little bit better what are natural numbers. So it is a good opportunity to to see how to work with them. So maybe, okay, so I will show you the beginning of this file. Okay, I will not go very far, just to understand the what is expected here. So at the end, we will use a list of numbers but as I don't want to mix up everything, I will consider a list of something else. I will consider list of colors because we like colors in these lectures. Okay, so our usual type here, and I have my own type of list. It is called list of colors, list C, and have the empty list of colors. So we call nil C and the cons C. Okay, so this is my the name okay. So you see that a list, okay, is either empty, okay. So nil C has nothing. It is like an enumerated type, nothing at the leaf, okay? Or a list could be made of a color, another list, recursively, and you get a list, okay? So exactly what I draw here, so except that this one is called cons C, and this one is called nil C, okay? So for people who are not in the room, I just show what is on the screen. Okay, so remember that you have this kind of trees but with only one branch in some sense, only one branch, only a right branch. Okay, it is like a binary tree without the left branch, if you want. Okay. And another number is like a list without the color. So we are simplifying things. So if you are able to play with trees, you are able to play with lists and with numbers. Okay, so once again, I give examples to play with. Okay, so here I have a list made of two colors, green and red. Another list with again two colors, orange and orange. Okay, and there is one very important function on list, which is called append. So we or concatenation first. This type here. Okay. So at concatenation, it takes two lists. So if you have two lists, you could be tempted to make two recursive calls. To make two case analysis, one on the first list and one on the second list. It's a bad idea. You only need to perform the case analysis on the first list. That's enough because you intuitively you will traverse the first list, and at the end you return the second list. You don't need to look at inside the second list. Okay, so let us look at this program. It is important to write it and to look how it is written. So append is here. So append, so I call my list U and V, okay? And if U is the empty list, the append of U and, sorry, the append of and V is just V, okay? If U is made of an element and a sublist, okay, I will append the tail U prime. Okay, so U prime, you can see that as the tail of the list, and X as the head of the list. So I append the tail of the list to V, and when it is finished, I add the element X at the root of the result. Okay. You could think that it is a good idea to make another pattern matching on V in order to see if V is empty, the nil list, then by optimization I can already answer that the result is U. You can try to do this, but I promise that you will get into endless complications. The simpler the definition, so don't try to make something which is in some sense optimized for some reason. You could believe that it is optimized, if you think a little bit more, you will see that actually the complexity in the general case is not that good, and you just have a more complicated definition, and it will make your life much more complicated to reason on the function. So the simplest the definition, the better. And if you try to perform the case analysis only on the second one, it doesn't work. You can try. Please try just to see what happens. But the solution is this one. Okay. So this is something to know. Very basic thing to know about list. The important operation is happen, and it is defined like this. It is asymmetric. You can see it is asymmetric because I traverse the first argument. The reason it is that lists are asymmetric trees. Okay, we have a branch on the right. So okay, so we can check that it is correct. So I compute L1 appended to L2. Okay, I should get the list green, red, orange, hopefully. Yes, it's a little bit small. Okay. So green, red, orange, and nil at the end. Okay, so you see the constructor. So okay, you can draw in your head the concept on top and root, and you draw your two branches. That's good. Of course, if you have a long list written like this, it is somewhat hard to read. So maybe we will see later some notation mechanism to simplify the reading. But you have to remember that lists are something which is like a branch on the right. It is very important because if you have a better notation, then you could see lists as something which is a little bit flat, like an array. It is not the case. Looking at the end of the list it takes time. It takes computation, I mean. Okay, so now okay, we can compute, but now it is good to have good properties on append, and basically there are three properties to know. One is that nil appending on the left return the same thing. Nil appending on the right return the same thing again. Okay, and we'll see that it is interesting to look at that. And the third important theorem is that concatenation or append is an associative operation. If you append, okay, so we'll see. This is the three basic things to know on lists. Okay, mathematically, we say that we have a monoid. Okay, so let us try the first one. So, oh, sorry, I have to. Okay. Again, I introduce L, my list. Okay. As usual, I have a function applied to a constructor. Okay. So you can get that here, the computation will succeed because of the definition here. I have the first argument. The first argument is known, is sufficiently known, so the computation can be performed, can progress, and I get L is equal to L. So you see that basically, okay, this is a very important thing. You could see that append is a recursive function, so you could say, oh, okay, I just do an induction. No. Not necessarily. In that case, no induction is necessary. Just reflexivity works. Okay, so don't rush on induction. Think that induction for sure could be useful. So okay, that's true. But sometimes it's even simpler. So no need to use induction in that case. Just simplify. And this is finished. Now, for the second theorem, which is neutrality on the right, it's a different story, because this time you see that what is known is the right argument of append, and in that case, I don't have enough information. In order for the computation here to progress, I need L, the left argument, to be to have a more precise shape. Okay, that's not the case. So if I try a CBN here, nothing happens. It's just okay, no progress. Okay, so in that case, yes, you need induction. That's normal, because if you think a little bit, you have an append. If you imagine, okay, forget about a general theorem. Imagine you want to compute counts of red, of counts of green, of counts, a list with 3 elements, and nil. You see that by this very definition, this computation will take 3 steps. You need to traverse the list 3 times, counts. Okay, I have a count. Okay, I will compute on a smaller list, which is made of only 2 counts. Okay, and then again recursively on a list which is made of only 1 count, and again recursively I find my list made of one of just the nil. Okay, in your head, and then I count the elements. Okay, on the stack, on the recursive stack of calls. If you have some knowledge on how to compile function calls, you know that you have a stack. So these 3 counts are in the stack, and okay, so the 3 elements are added on the result one by one in the reverse order. So you get what you want, but the important thing is that when you append a nil as the second argument, you have to work. Okay. While if it is on the left, there is almost no work to be performed. Okay. So as you have to work, that's the same for reasoning. You have to reason by induction. Okay. So induction here. And now you have to think, oh, okay, this is induction on lists. So how should it work? So induction, it is like a destruct. So induction on L as, so I have how many cases? So as many cases as the number of constructors. How many constructors for lists? 2. Okay. So I have 1 constructor with no, so 2. Okay. So let us write 2. Okay. 2 cases to be considered. Now, first case is nil C. How much contents in nil C? Nothing. Okay. So this one, no contents. How much contents inside the count constructor? I have 2 things. This, okay. So I will call it. Okay. I will give a name to these 2 elements. So one is X. The second one, or I could call it L prime if I want. Okay. Okay. A name I choose, and I see that the second component. Okay, sorry. I should look here. Okay, here. I see that so first component, second component, it is a list. It is a list, so which means that I can here use an induction hypothesis. Okay, so each time I have something which has a type considered, which is defined here, okay, I have an induction hypothesis, a corresponding induction hypothesis. So for trees, I had 2 induction hypotheses because I had 2 subtrees of type AST or something like this, or bin tree yesterday. Okay, but here for today, for the list, I have only 1 recursive call. Sublist. Okay, so this list is called L prime. So I will have 1 induction hypothesis on L prime. Okay. So I think that my scheme is correct here. Okay. So I get my two expected subgoals. The first one is about, okay, but now you see that induction is performed. Induction considers the two possible cases for the first argument. So I have the first argument, which is known now, so I can compute. So let us compute. So there is only, so I can be lazy. There is no danger here. Okay, nothing to worry about. Let us compute. And when I have this one, I return the second list. The second list is nil C. Okay, so I get nil C on the left. I keep nil C on the right. So induction. Sorry, reflexivity. Second subgoal. Once again, the first argument of app is a little bit known. So you can see here the X and the L prime I gave here. Okay, so this is a cons of X and L prime. So I get it here and also here, by the way. Okay. Okay, so have this L and this L have been replaced by cons XL prime. Okay, here and there. Okay, so this is the induction scheme, and then I have an opportunity to reduce the function append. Okay, so and nothing else to compute. So no problem. No need to be very precise here. No danger. So this one will be computed. I will get by definition. You can see I will get by definition. So consi of sorry U. So U is this. U is this one. So I will get the consi of X and recursive call up and L prime and the right hand side, the right member of the second argument of app, which is here. Okay, so just by reduction. Sorry. Okay, by reduction. Okay, you see the computation which progress a little bit, and now, as usual, I have an opportunity to use the induction hypothesis. So I can rewrite it. I will get L prime here, and I will be happy. So rewrite my induction hypothesis. Okay, and we are done. Okay, so okay, third essential lemma, app is associative. So this theorem looks threatening because we have three, not one, not two, but three lists. Okay, so you may be afraid that okay, you have 8 cases, 2 cases for each one. So maybe 3 inductions consecutive with 8. Okay. And actually, if you defined app in what you would believe an optimized way by saying, oh, okay, here, let us say here, I have 2 cases for U, 2 cases for V. I will have directly the U concatenated to V to nil is U. Okay, you believe that this is a good thing. If you program this way for associativity, you will actually have 8 cases to consider. But I have been more careful here. I define app only by recursivity on the first, by case analysis on the first argument, and then recursivity. So maybe the induction will be simplified, and actually, if you think a little bit, you see that you have app U. Okay, so for sure you will need to make an induction on U. Maybe on V as well, because you see that, but actually you will see that just a simple induction on U is enough. So if your definition is simple enough, your induction will be very simple. So let us. Okay, so associative. Once again, maybe I forgot to explain the meaning, but okay. I mean, okay. So if I append first the two last and then append U, then I get the same result if I start to compute this one and that one. Okay, before doing the proof, I would ask you why this theorem is important, even from a practical point of view. By practical, I mean if you think about computation time. So the question is, imagine that you have 3 very long lists to append. What is, okay, here we have 2 ways to append this list. I could append the first one and then the third one, or I could write, so this one looks strange. I start to append the second and third list, and then I append the first on top of the result. Which way are they? Okay, question, is it equivalent? Does it take the same time, or is one of these two options better than the other? So, in order to have some hint, you need to remember how app is written. You remember, so the only thing to remember is that app traverse the first list. Okay. If the first list is empty, is nil, the computation is finished. Okay. If the first list is very long, I will take as many steps as the length of the first list. So basically, it is a computation, and whatever the length of the second list, I don't care, because the second list is not examined, is not okay. So you may consider maybe an interesting case where the first list is long. For instance, 1,000 elements. The second list is very long, also 1,000 elements. And the third list, I don't care. So the third list, okay, 0 element. So, for instance, if I compute this one, okay, so 1,000 elements and something. So, okay, so I will take 1,000 steps here, and I will get a list which has which of length 1,000. Okay, so 1,000 steps to compute this one. And now for this one, how many steps? This one I said it has also 1,000 elements. So altogether it will take 1,000 steps. Altogether, this computation takes 2,000 steps. Okay. Now take this one. I compute this one, U and V. So I don't care about this one. The only important one is this one, 1,000 steps. Okay, so I get 1,000 steps here, and the result has 2,000 number of elements. 2,000 elements, sorry. Okay, so in order to compute this one, I will take altogether 3,000. Okay, so you see that the result is the same, but the computation time is not the same. So when your program is append, you should be careful. If you have several lists to append, okay, this is the right order from right to left. Not the intuitive one, by the way. It is not when you compute with additions. Okay, usually you say, okay, 2 plus 3 plus 10, you say, okay, 2 plus 3, 5, plus 10, 15. This is the usual order. And by the way, because I think I will not have the time to go to natural numbers, you will do the, okay, basically, all the theorems, important terms on the list have something which correspond on natural numbers, because natural numbers, as I said, are like a list, simplified list in some sense, okay? But that's the same, if you compute 1,000 plus something, okay, but it's better to write the thing in this order. So which means that the implicit order given by Koch is the wrong one. But because actually this is just because anyway, don't use Koch. At least don't use this representation. So this representation actually is excellent. It is the right one for reasoning on mathematical numbers. Okay, this is only for reasoning. If you want to do long computation on numbers, okay, go to another representation based on the bit string, this kind of things. Okay, Koch has some stuff for doing that. But okay, but if you don't need complicated things, you want just make some computation on okay reasonably small numbers, even 1,000, for instance, you can keep this representation, but it's better to compute the addition in this order. It is exactly like the append. Okay, that's enough for the importance of the theorem. Okay. And by the way, okay, we will see later next week. For other functional lists, such as reverse, for instance, it is easier to write the reverse of a list. Yes, rather easy using the append operation. This is a natural way to write it. But there is another way which does not use append. And if you don't use append, it is better for exactly the same reason. Okay, so let us introduce our three variables, u, v, and w. And now what I say is that as app performs case analysis on its first argument, okay, then we will just perform an induction on u. Okay, so once again, so induction on u. So two cases as before, like before, nil without anything, and then counts with an element x, a sub x, I call it u prime. Okay, maybe I will be more, okay. So use this name, induction hypothesis on u prime. Okay, and I have my two goals. And then actually you will see that everything is easy. Okay, I will, okay. One thing you can do, for the same reason as before, you can do the CBN, and instead of repeating CBN, okay, this is, I know in advance that CBN will be performed in each case. So I can do this, I put a semicolon, this sign here, and some tactic, so here CBN, which means that on all sub-goals, perform this tactic. So this time you will see a simplified goal for the two cases. Okay, you see? For example, for first case, you just see, okay, append is equal to append. Okay, so you see that, okay, so here. So you see, okay, no need to simplify again, just reflexivity. Oops. I lost my, okay. And for the second one, let us look at what we have. Sorry, the second one. Okay, we see, okay, we see consi of x. Consi of x, okay, it starts the same. And then we have this, which is exactly the left-hand side of this one, and that, which is the left-hand side of that one. Okay, so you see reflexivity, rewrite. Okay, so you see the proof actually is completely trivial. Okay, just so you see that a very simple induction will work in this case. Okay, Then, yes. So here is a simple exercises on reversing a list. Okay, so this is the standard way of defining reverse. So you will append in the recursive case the reverse of the tail, and you append the reverse of the tail to the list made of one element. Beware here, it is not the element X, it is the list made of one element X. So if you write here X, it will be caught by type checking anyway. So okay, then you can prove these things. For example, you can prove that the reverse of append is the append of reverse in the other order. Okay, and then so you need this theorem if you want to prove this one. And here you see that this is something which looks like the theorem that we had on binary trees the very first day, you remember? On binary trees, I was able to define a reverse function. And what happens that you can see that actually the theorem on binary trees is much easier to prove for lists. Okay, that's one of the reasons I prefer to start with trees rather than lists. Lists are for things like this a little bit more complicated. You need an auxiliary theorem, and you need also this append intermediate function just to define what is reverse. For binary trees, you don't need an auxiliary function. Okay, so binary trees are simpler than lists for us. Okay, and then you can continue on natural numbers. So you have basically the same. You have the 0, you have the plus, and you have the plus is associative. It is exactly the same shape. And and there is another thing that you have on numbers that you don't have on lists, which is commutativity, of course, because if you append two lists in one order on the other order, you don't get the same list. Okay. But for addition, you get the same. So one of the basic thing on addition is that n plus m is equal to n plus n. So this is one of the very basic things. So these theorems are not difficult. I would say they are even somewhat boring, but okay. So okay, these are very good exercise for practice. Okay, and then you can also relate list to numbers by defining the length of a list, and you can prove. So this is yet another very basic exercise. Prove that the length of the append is the sum of the lengths. Okay, so something quite intuitive. Okay, so you can basically should be able to do that quite quickly. Okay, and the good news is that okay, actually these natural numbers are defined in code. So actually, so these are I redefine natural numbers here. I redefine them. If you look at here, okay, I define them in this way, and this is actually exactly the definition of flow. So you see, this is exactly what I wrote here. You have the 0. Beware, it is not a 0, it is a O, capital O. Okay, because it is a constructor. So constructor are made of letters. So capital O and capital S. So S of O, okay, represent 2. Here I get, okay, this is my number, so I get S of O. If I do the same later here, okay, print nat, okay, so nat, it is the same in Coq, it's exactly the same definition you will see. But now, if I check S of O, or if I write this, I define 2 is equal, I want to prove that 2 is equal to S of O, because actually the standard library adds some notation, convenient notations. If I write this, actually I see 2 is equal to 2. So what? But actually, what happens is that what is written to is actually S of O. But Coq, when Coq sees S of O, okay, he says, okay, the way for printing that is 2. So, okay, so for 2 days, it was maybe a little bit misleading to you because I used 1, 2, 3, 6, even 8. Actually, it was S of S of S. Okay. Bon. But I did not need actually to reason about numbers. So I just use them, okay, for doing intuitive things. Okay. But now you know that numbers, there is nothing magic. It is defining coq and etc. So you have a full library with plenty of things. And here we gave you a number of tricks, because as you guess, you have many functions, not so many functions, plus addition, etc. But also you have many theorems which say that, okay, for instance, distribution of multiplication, etc. All the basic mathematical laws, you know, are proved in advance in the standard library. You could do the exercises or not, or just use the library. Okay, and using that, now we are able to define our arithmetical expressions like that. And so I use the standard NAT of Koch. And so beware that the NAT here, I will stop with that. For the rest, I think you will you can progress by yourself. You have a few days. So beware one pitfall: the NAT here and the NAT there don't mean the same thing. Okay, this one is the constant as before. Okay, the constant 3. Okay. Here I am talking about a variable, and the point is that, okay, to run into complication with strings, this kind of thing. I could do that, okay, but for simplicity, I will just say that I have variables whose intuitive name is x0, x1, x2, etc. I just represent, for instance, x2 by the number 2. Okay, so when I say AVA, I don't know how to pronounce this in English, AVA, something. Okay, this thing applied to 2, it means the variable that you would call x2 in your favorite programming language. Okay, I have only these names. It will be enough for introducing the important things. Okay, so that's all. So you can have expressions which have constants and variables. Okay, and things that for the state, okay, and the state will be actually a list. Okay, so I already find my own list. I think, yes. Later on, we will use again the standard list of Koch, but okay, this is just because. Okay, yes, okay. One thing that the standard list of Koch are actually list of anything, but list of the same anything. Because I want to define, for instance, the append function. Append function that works the same for list of colors, for list of numbers, for list of functions, a list of, okay, you have a list of whatever, but list of the same thing. So the real list of Koch have an additional parameter. I don't want to complicate your head with that at the moment. So I just want to have a list of natural numbers, and I call this state. Okay. We could also list. Okay, so a state will be a list of numbers, and that such a list contains the value associated to respectively x0, x1, x2, etc. in that order. This is the convention I use, and using this trick, my states are very simple. Okay, but actually it is like the true memory you have in machines. In machine, you have a state made of consecutive. Except it is not a list, but it is an array, but it's the same idea. Okay, so in a real state, you have an array of values. Okay, and you say that, okay, this array corresponds to consecutive cells. Okay, so this is I have the cell for the x0, the cell for x1, the cell for x2, and so on, and I have a default value which is 0. Okay, So with this convention, the handling a state will be very simple.
If I write the program, you only use one variable.
Yes.
It's called x100. Then
No. Okay. So you have a program which, with the variable called x1. That's what your point.
normally you say x1.
Hmm?
Normally you name this variable to x1.
Yes. Yes.
But if I just want to name it as x100.
Yes. Okay. 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 Okay.
100.
Okay. Okay.
Then the state will have 100.
Yes. 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 I agree.
That's bad.
That's bad for computation. Yes. Yes. I agree. That's bad for computation, but I don't really intend to perform real computation. Yes.
Yeah,
Okay.
yeah,
It can be done, but in that case, okay, be a little bit careful. Try. Okay. 100, I think code will manage, but it is 1 million. It will be bad.
Yeah.
Okay. But for reasoning, I don't care. For performing proof, I don't care. Okay, maybe I still have almost 10 minutes. I would like to. Okay, maybe I finish on this one. I would like to go back to my introduction of yesterday because I added some material here. Nothing which requires proving anything. It is just text explanations. And it is in several places here. So I will just go this is not when I see things just code. I just go here. Okay. So I think we look at this code yesterday, so nothing new here. Okay, so we saw this wow function here, I think. Okay, so yes, so we see a function which returns not a value or not an ordinary value, but it returns a type. Okay, so we were able to define it, and then we were able to use it, and I have to add something here. Okay, we're able to use it, but okay, we were careful on the this is not an arrow, but it is a for all. Okay, and then nothing new at this point. Okay, this was this was said yesterday. I can print it. I think there is. Okay. I don't know why a proof general is. I need to display explicitly. Okay. Oh, so I get it. So okay, nothing. Okay, nothing. Yes. Okay. Here I put the return, but if I don't put it, Coq will print it. Okay. This is okay. So nothing new here. Okay. Now, did I show you that? I'm not sure. This definition here. Maybe not.
No.
So, okay. So a few words on this one. So I do something which is very close. Okay, yes. I want to use my new power, which is define functions with a type using the for all, so what we call a dependent type. And I want to define this thing. So basically it is a theorem, okay? The theorem which says that C is equal to next call of next call of next call of C, okay? 3 times. So we have seen yesterday that this theorem can be proved using destruct followed by reflexivity. And actually what we get is exactly this code. So your fancy corresponding to the for all, okay, so or the intro in interactive mode, and then the destruct is corresponds here to the match. Okay, it is destruct actually makes a match. Okay, and the reflexivity here is just given by eqref and eqref without underscore because I am in a cleaner state than in the other file. Okay, but anyway, I don't want to comment too much on reflexivity here. The point, okay, I could actually. Oh, okay. Because I put this, I did this stuff which is wrong. I need to, okay. So here it's okay. Okay, I don't import anything complicated. So I have a simple eqref, and if I, okay, I say that this eqref is misleading. It intuitively says that it is reflexivity, but actually it is something which should depend on green, depend on orange, and depend on red, if I want to be very precise. So if I add this command set printing all, actually Coq will print more things, and you see that the real function here is like this. You see it is eqref with an append, with the arrobas here to say, okay, the full thing applied to green and also the color, okay? So applied to green, to orange. So you see that the actual thing here depends on the case, okay? So just to show that, okay, there is no cheating here, actually. So I remove this printing all to keep things simple to print, shorter. Okay, and the next point I wanted to show you is that usually for the theorem, we use QED instead of definition or definition followed by defined at the end, refine, okay? And this QED is very important. It has an effect that you have to know. The effect is the following. So let us see what happens. So I consider exactly the same theorem as before. Okay, same statement, but instead of definition as before, I do like yesterday, proof, intro, followed by destruct, followed in all cases by reflexivity. So this is a very short proof, but basically the same as before. QED. QED, not defined. If I put a defined, I will have a different effect. So now, if I compute my previous function, which was defined using definition, if I compute it applied to some argument, so it could be green, or it could be another expression of type, of the right type, okay? So I apply to next color red, okay? What I get is next color red is equal to next call of next call of next call of red. So I mean, oh, sorry, we cannot see everything. So I will copy paste it. Here. Okay. So we see that the type is exactly what you have here. C is equal to next, okay, applied, but applied to next color of red, okay. So it computes the result, and the result is okay. Sorry. The result you get here, you have to look here. You get an eqref. You get a proof by reflexivity, okay. But now, if you compute the same thing on the QED version here, you get the same type at the end. That's normal. But the point is that the proof you got is not a proof by reflexivity. It is just to say, okay, my proof is apply this function to, okay, he computes green, okay. He makes some computation here because next call is defined as a function. So computation is performed, it is green, okay. But this function cannot be computed. So the thing you have to remember is that when you write QED here, you say, I have a function that could be used for computation, but actually it is a theorem, and for theorems, computation are not that useful, And Koch actually remembers that, okay, it is not needed to make a computation. It is much better like this because theorems seen as functions could be the opportunity to many computations. And you really don't care about the final result. Okay, it is an equality. You can guess that at the end, a proof of equality needs to be, when it is in standard form, the canonical proof of an equality is always a proof by reflexivity. But okay, we can. It is enough to remember that is applying this function to that. Okay, is also a proof which is not computed, but okay, it is a proof tree for this result. For this result, okay, we see is an extra of one. Okay. Now, so if the thing to remember is that thanks to the Curie-Howard correspondence, we have a framework which is very nice because it is uniform way about talking about proofs and functions. I mean, functional programs. However, there are for different uses. Okay, so the second thing is that thanks to this correspondence, verifying that the proof is really a proof of what you say, it is just an instance of type checking. For instance, okay, at the end, this thing is a proof of red is equal to next call of the same. Okay, so by computing or not computing, I could just say check this thing. I will okay. So let's say check here. Okay, that's enough. I don't want to compute, but I see that I have a proof, a suitable proof of this equality. Okay, this is the proof, but I don't care. What is important is the result. The result is the equality. The equality, okay, that you guess. Okay. Sorry, I want to go back to here. So you see that type checking is very important. So we have both computing, a language for defining computational functions, okay, functional programs, and we have also these programs are typed, and type checking is important not only for the functions themselves, but when you interpret theorems and proof of theorems as statements and function. Okay, if you see them in the functional way, then checking that you actually provided a proof of this statement is exactly, it is only type checking. So this is very central. Now you have a function. You could compute with it, and it makes sense for computing colors, numbers, lists, etc. It makes sense, but computing on proof of theorems usually is not that useful. We will see it is useful in very specific situations. We'll see that later, but in most cases, it is not useful at all, and even probably a little bit bad. So for this reason, there are functions that could be performed but are not computed. Okay. And one thing is that another thing is that they could be performed, but still we have to make sure that if they are performed, you get a result. That is, the functions you define must terminate. Because if you were able to define programs corresponding to functions, you believe that you define a function like this one. So this one you can define in OCaml. So next function f, and you just make a recursive call to the same C and add something on top of that. So you return next call of next call of next call of next call of okay, without end. you know that this is an undefined function. From if you think to the denotational semantics of that, okay, it has no meaning. Okay. So this is strictly forbidden in Coq. You cannot try. You say Coq will sell you. Okay, no, I don't accept. The only possible recursive functions in Coq are structural recursive functions. Okay, so that I show you. You remember eval is called on a subtree of the whole tree. Append is defined on a sublist of the input list, and so on. Okay, and the same for numbers. So only this kind of recursion, and then you are in a situation where okay, so all the rest makes sense. Otherwise, it doesn't make sense. If you allow that, you get just an inconsistent logic. Okay, and even an inconsistent. This is not only on the logical side, but also even on the computational side that you have something which is inconsistent. So at the end, you have functions for proofs and normal functions, I would say. And actually, you have a difference, okay? The difference is that for theorems, the types are in what we call a universe, or a sort more technically, which is called prop, the universe of propositions, which is in the air, okay, and which is different from the universe of real data, which is called set, okay. So, for instance, if you check this theorem, this is the only one I have here, you see that this statement has the type prop, not set. Okay. So what? Now, okay. I could define. What I say is that actually, theorem, what happens in the real world. Okay, when you define theorem, of course, you want to reason by case induction on what is this object in the real world. But conversely, the real world cannot see what happens in the assertions. Okay, the assertion cannot be used for the computation. So let us see how it works. Let us define another color, but in prop, not in set. Okay. That's funny. So the same, but I call them eye green, eye orange. Okay, they are hidden, okay, or invisible. Okay, let us try something. I can compute an invisible color from a tail color. Okay, so as it is something which is in prop, I will call it a theorem, but I could call it in definition if you want. Okay, but okay. Just to insist that it is. So I can say it is like a function. It is a TL color, and it returns an invisible color. This is allowed. I just reason by case for this one. I return an invisible color, which is different in each case. Okay. So eye green for green, eye red for orange, and eye red for red. Okay. Okay, we could print it if you want. Okay, this is definition. Okay, match, etc. Okay, but if you try the converse, it is impossible. I want to try to define the same code here by destructing an invisible color to make a color. Let us try. Introduce our C, and I want to make something which is in set. While this one it is a prop, okay. What I get, this is one message you have to know. This command has indeed failed with message. Case analysis on sort set is not allowed on inductive definition TL color. Okay. Okay. Maybe I should show it here. Okay. For inductive color, okay? So it means that it is impossible to Okay, it is okay. It is written this way. Okay, I cannot make something to make a set from a prop. This is that's what it means. Okay, so assertions are supposed to be okay. So assertion. It is like in security. You have a high level and low level. Okay, so propositions are high level. They see everything. Okay, but the real thing is a slave. They cannot see assertions. Okay, so okay, so this kind of message can happen when you mix theorems in and definitions, recursive definitions or not. By the way, it's not just it has nothing to do with recursion. It has only to do with pattern matching actually, because it is when you perform pattern matching that you analyze where you are. Okay, and then okay, sorry, I'm not a bit long, but I'm almost finished. It is finished, the Zoom?
No, it's not finished.
Okay, but okay, so it takes room, but it actually it is very short. Let us define our wow like before. Okay. So I take a tail color, I return a set, so everything is fine here. And so this is the one which is on a set. Remember, I return a set which is nat for green, tail color for etc. Okay, so the same definition as before, but the difference is that I say here QED. So it is a set, but I say QED. Okay, because okay, I am too fast. Okay, it is allowed. Okay, but now the funny thing is what follows here. If I try to reuse my definition of before, which returns a wow of C with the same thing, okay, green, in the case again, I will return a 2 for orange, okay, a color here, and for this one, I should return a function. Exactly, it is a copy-paste of my previous definition, okay? This will fail. Why does it fail? The reason is that in order this to work, type checking needs to compute this expression in each case. It has to compute, it has to check that wow QED of green, for instance, returns nat. So the other function, okay, wow QED is equal, but with this QED, I prevent Coq to perform the computation. So the computation cannot be performed here. Okay, so Coq will say, the command has indeed failed with message. The term 2 has, okay, we cannot see. Let us see the message. Here. The term 2 has type nat, while it is expected to have type wow QED of green. Now look at your definition. The definition is here. Wow QED of green, what of green? Yes, it is not. Huh? So wow, it is. I am expecting the nut, but you provide me this. So you say by conversion, it is the same, but here you prevent the conversion to be performed. So Coq is not able to perform the computation. So the purpose of this demo is to show you that in order, usually you don't write that, of course, you write definition, the colon equal, etc. So you don't even see the problem. But the point is that actually this shows that Coq, in order to accept this kind of definition, has to perform the computation, which means that at that type checking time, you have conversions. If you prevent conversion, okay. So the consequence is that, once again, as we want type checking to be decidable, in order to be sure that are those theorems are really proved when you because as I said before, a proof of a theorem, you type check the proof, you type check the proof tree, and that's this proof tree. Okay, and so in order to perform type checking, you need in order to verifying that your theorem is proved, you need type checking, you need decidable type checking, and as type checking use conversions needs to terminate all the time. Okay, so this is why in Coq we don't allow any kind of programs. We only allow programs which terminate for sure. Okay, this is called, in theoretical papers, it is called normalization. Or actually, weak normalization is enough, but we have even property which is strong normalization. Basically it's strong normalization, but in some corners of Coq, it is not completely strong. Strong means that actually, whatever the order of the computation, the result will any strategy will be satisfactory. Okay, but we don't need to worry about that. So important point is that computation is important, and so we are limited to terminating programs. So it could be good or bad. It is good because we are sure that any program which is accepted by Coq terminates. So it is a good security. Usually you want this property, but sometimes we also need programs which do not terminate. Okay, so it is. For instance, so we can play with conjunctive things. But another thing is that sometimes you have programs which happen to terminate only in complicated situations. And in order to deal with that, it's not that easy. So I expect to show you. So this is one of my research topics. So I expect to show you a way to deal with this situation at the end of the lectures. Okay, so I think that it is just remembering, so you can read it. So clear forward, it is just that proof is equal to function program. Formula is a type. Provide a proof. So this is the activity. This is write a program basically. Maybe a program which will not be performed, not really computed, but still you write a program, and checking that P is indeed a proof of T is type checking. And all the rest comes from that. Okay, and what I told you about in the last part, it is called the conversion rule. It says that, if P has type T, and then P has also any type T prime, such that T reduced to T prime, or conversely, in more generic cases, go in the two directions, or T and T prime reduced to the same thing, basically. Okay, but anyway, by computation, when I say reduce, it means equal by computation. It is not a theorem, it is a computation. Okay, so this is one of the subtle and important points of the type theory behind Coq. Okay, so thank you for attending until this end. Sorry to be such late.
Okay, thank you. Even though it's late, I still have a question. Can you go back to the definition which fails?
Yes.
And then how to make it work? You have the cursor is in the fail.
This one? No. Avant?
No, fail. Fail. Yeah, fail definition.
This one. Fail.
Then how to make it work?
How
to change it so that
this definition is dead.
Because
here the problem is that you want this type. You want the type of the result has to be there, and here you are dead because this the way it is defined is bad. So you have to go back here and say here defined,
defined,
and then then fail definition fails.
Yeah.
I mean, here you cannot this. Ah, no, it has not failed. It is good.
Yeah,
So
it should be good.
okay, now it's good.
Okay.
Now it works.
Fine, instead of two.
So this is yes. The point is to use define. And okay, so this is why sometimes in the Cochlist you see people complaining. I would like these things to be defined and not QED. How to change that, etc. Okay. Because sometimes you define a lot of theorems. Okay. And at the end, you need this theorem to for making something for helping you to make a computation. And if after 2,000 million lines of theorems, you have to change all your QED by define, you are not happy.
Again, and then
Okay.
finish the.那个会上没结束。Yeah, you can stop.
Yes, I will leave the room.
About the because I wasn't distracted. Can you go up?
Ouais.
I didn't stop them. Maybe we can stop the.
Ah, pardon.
Yeah, the group training.
End.
You can end the meeting.
Okay, end meeting for all. Allez, hop.